Hello everyone, I am Suyuan Wei from McVie Technology. I am glad to share our work, joint token pruning and squeezing towards more aggressive compression of vision transformers in CVPR 2023 here. We call it TPS for short name. Let's start from a quick preview of our TPS. We focus on pruning tokens in vision transformers more aggressively and efficiently from the perspective of saving information loss. As you can see in the left figure, the first row shows some cases that a vision transformer model predicts rightly, but in the second row, we prune some tokens and get wrong but somehow close answers. Moreover, we find the performance drop back become more severe along with more token being pruned. For a fair comparison with prior methods, and also to show our flexibility, we designed two variants of our TPS, including DTPS and ETPS, one for the interblock pruning and another one for the intrablock. They are both easy to plug in vanilla or hybrid VITs. As you can see, they both pass the two baselines and other state-of-the-arts, and show higher robustness under our random experiments. Okay, let's start from some basic knowledge of vision transformers. It's a popular model architecture from NLP with strong performance but higher computation cost. Differing from CN's sliding windows, it processes images by splitting them as patches. We call the vision transformers that follows most original designs as vanilla VITs, such as DIT and LVVIT. The recent works also borrow some design from CN, such as some hierarchical operations or convolutional layers. Here we call them hybrid VITs. There are already some works that prune the redundant tokens in VITs. Patch slimming and dynamic VIT learns to drop tokens dynamically based on the input images, which leads to context information loss. Moreover, EVIT compresses the originally pruned tokens as an extra new one, but it's not enough when meeting more aggressive compression. The recent work, such as ATS, learn to prune tokens with input-dependent number more dynamically, but it needs to a long constant shape model. In the left figure, we show the wrong predictions brought by pruning in ImageNet 1K, which we also mentioned earlier in the quick preview. In the right figure, we show toy experiments to illustrate the prune tokens information is worth saving. The bonus accuracy comes from we use prune tokens but not the reserve tokens in the first pruning layer, although it leads to a terrible performance drawback. It also gives some extra right predictions. Here, we'd like to introduce our TPS. More specifically, the figure below compares our TPS with prior token pruning and token reorganization. Our TPS preserves information from prune tokens by squeezing them into reserved tokens dynamically. Notice that we also maintain the constant shape of pruned models and bring no extra tokens. Our TPS employs two steps, include pruning and squeezing. The first pruning step follows dynamic VIT and EVIT for fair compression. The DTPS uses the learnable scoring, while the ETPS follows attention scoring in EVIT. For the second step, squeezing, it contains two parts, including matching and fusing. For the matching step, as you can see in the left figure, that shows the real matching result of a snow leopard picture. Each prune token matches with its most similar reserve token. So you can see it's a many to one way from the prune token subset to the reserve token subset. Giving the matching results, which we record it in a mask for regular matrix operation. We conduct a similarity-based fusing way to inject Pruning tokens into their matched reserve tokens, which we call host tokens. More similar a Pruning tokens is with the host token. More higher weights it contributes in the fusing step. And also, the rest long-matched reserve tokens remain the same. Okay, the method part is over, and we'd like to show our experiment results in the following part. We compare our two variants with two baselines, respectively, and we surpass them under all pruning settings, especially larger margin, along with more aggressive compression of Pruning tokens. We also compare the efficiency of our methods with other state-of-the-art vision transformers and other token pruning technologies from the perspective of accuracy and computation trade-off here. We also find our method can benefit from longer training epochs and even surpass the pre-trained models. In our ablation study, we show some different choices in the matching and fusing step.